I'm pleased to join you today in what is the first of what may become a series of presentations involving aflatoxin risk management. And in this presentation, I'll follow a storyboard format, beginning with the history of the Office of the Texas State Chemist, and then discussing aflatoxin test kit validation, some sampling study work that we've done in Kenya, the use of reference material which addresses traceability as well as managing variability, and finally going through our proficiency testing program, which at the end of this presentation I'll introduce you to how you can register for this and participate in a global aflatoxin proficiency testing program. In terms of the history of our office, we were founded in 1899 with the Texas Commercial Fertilizer Control Act, and then in 1905 the Texas Commercial Feed Control Act. Ours is a fee-based agency. Essentially, at present, 22 million tons of feed are manufactured and distributed in the state of Texas, and our inspection fee is 19 cents a ton, and about 15% of this revenue goes toward aflatoxin and other mycotoxin risk management. Based on our law, we see that whole grain is exempt if it does not contain a toxin. So by de facto, and one could reasonably surmise that if it does contain a toxin, if whole grains and whole seeds do contain a toxin, they fall under our regulatory authority. Our mycotoxin limit, or aflatoxin limit, is 20 parts per billion. And then we have upward ranges for different animal species where the whole grain or seed can be channeled to ensure safe consumption and also protect human food safety as well as animal health. We've been regulating aflatoxin for a number of years, as evidenced by these bulletins that date back to 1991, involving licensing, labeling, and in 2011, the state chemist approved blending. Also significant in 2011, we launched what has been referred to as a co-regulation program, going by the tag name One Sample Strategy, in partnership with the Risk Management Agency of the United States Department of Agriculture. And the Risk Management Agency is the agency that administers the federal crop insurance program. Our aflatoxin risk management program is comprised of these 5 pillars that are built on a foundation of laws, rules, standards, and official methods, and government-backed codes of practice or action plans. And our 5 pillars include crop insurance, and that will be an important part of our study, our story, first story, and how we interact with the risk management agency. Also, inventory tracking and reporting. This includes both establishments as well as, we'll see, contaminated product. The overall thrust of this presentation will focus on lab quality systems and how we discovered there was a need to implement that in the Texas grain industry. And then also I'll talk about some of our surveillance and monitoring data and communication outreach. These pillars uphold what we now describe as a public-private partnership with shared responsibilities and mutual benefits, with the resulting development of a connected and transparent marketplace. I want to begin this story with an incident that occurred in 2005 based on a report by the Office of the Inspector General in 2007. In particular, this report is an audit of the Risk Management Agency involving their crop loss and quality adjustments for aflatoxin-infected corn. As evidence on this slide, nationally in 2005, the approved insurance providers, or AIPs, paid indemnities for aflatoxin-infected corn totaling $27 million, of which $17.5 occurred in Texas, highlighting the magnitude of the problem here. And for 394 of these claims, the OIG found that the AIPs paid extremely low values, from 8 to 25 cents, when later the producers sold the infected corn for prices between 80 cents to $2.30, or 5 to 28 times the value calculated for the indemnity, resulting in unusually high payments to the producers for crop insurance, as well as close to market values, at least at the upper end of $2.30 for the corn. As you might imagine, there would be a public meeting, and there was. It occurred in Austin in 2007 following the release of this report. And at that meeting, I forged some good working relationships with the risk management agency personnel that continue today. And they are essential to this first story. Moving forward to 2009, we encountered a situation where there was a bankruptcy involving a shortage of grain inventory that was discovered by the Texas Department of Agriculture's Warehouse Examination Division. Our agency was interested in this event because we had seized several bins containing high aflatoxin maize. And as a result, I petitioned through public information access the report by the Warehouse Examination Division, and was surprised to find that there were over 500 third-party analyses of maize for aflatoxin for the purposes of crop insurance. And so during our surveillance and monitoring, we might get 3 to 5, maybe half a dozen maize samples that we would test. But now I found that there were hundreds of those already performed, and found that they were very similar to our results. Because the results of these reports were extremely high, I petitioned the court to manage the disposition of this bankrupt maize, and was granted that. I negotiated terms with the bankruptcy attorney, essentially involving testing the first 5 loads out of each bin, and if they were over 500 parts per billion, the entire bin would be evaluated, and anything over 500 parts per billion would be disposed of. And we ended up burying 73,000 bushels of maize due to aflatoxin contamination in excess of 500 parts per billion. During our planned disposition of testing these bins, it would have lent itself to a variance component analysis, and resulting in publication of these variance components as the grain was reclaimed from all 6 facilities in each of the bins and truckloads. And so what we see is we characterize the variation or source of error as well. We see the facility contributed very little to the variability structure. In other words, all 6 facilities had equally high levels of aflatoxin contamination. We found bin was the major contributor. Almost 66% of the variability would be explained by bin in our mixed model analysis. And then truck was about 9.1% of the variance, and then sampling and testing error explained 23% of the variability. So we found some interesting things through this bankruptcy case. One, we found that there are additional tests beyond ours for regulatory purposes that are being collected that could be quite valuable in terms of managing aflatoxin risk. And so we began to question how we could access those and work more closely with the risk management agency, since we had shared interests in the overall management of aflatoxin risk. Another interesting discovery was that based on this result and some additional work, comparing a single probe with a standard 7-probe pattern out of each truck, we found that we had almost equal predictive or inference capabilities with a single probe versus a 7-probe sample pattern, leading us to conclude that the amount of variability from truck to truck was not that great. And so we entered into the 2010 year with several ideas about how we could evaluate and manage aflatoxin risk, working with the risk management agency. And so we, our investigators during the harvest, evaluated each of the facilities to see how closely they conform to the Risk Management Agency's Loss Adjustment Manual, referred to as the LAM, which prescribes the application of USDA sampling and testing techniques. And what we found was that fewer than 20% of the facilities collected samples with more than 5 or more probes, which suggested that they weren't actually following the Risk Management Agency protocol when they were collecting samples for a crop insurance evaluation. We also evaluated other procedures, including some of their testing procedures, and what we found was that there was an opportunity for improvement. Some of the other things that I would like to talk about when we look at this particular map is that, which is part of our surveillance and monitoring. In 2010, we had an extremely high level of aflatoxin contamination, highlighted by these different colored counties, where blue is greater than 500 parts per billion. And you can see from this we had 7 of those counties containing that level of contamination, followed by red, which was between 3 to 500, yellow from 20 to 300 parts per billion, and then green, less than 20 parts per billion. And so this was an example of an extreme case of aflatoxin contamination. And because of that, we decided to evaluate how well the facilities were doing testing for aflatoxin. I worked with the president of our Texas Grain Feed Association, letting him know in advance that we were going to work with the industry to evaluate their testing capability. And I say work with the grain industry, work with his members to see how well they could test. And we had a fair amount of cooperation with our 50 parts per billion, as designated in this table, 52 parts per billion aflatoxin control with 38 measures. We found that overall the facilities did a reasonably good job testing based on the average, which is 50 parts per billion. However, if we look at the low and the high, we see that the lowest value was 2 parts per billion, and the highest value was 102 parts per billion, which frankly was a little discouraging working with this reference material that was presented to them in a 50-gram package. There were some other things we asked them to do, including testing their scales to see whether they were working accurately, and some other items involving testing, grinding. We found a relative standard deviation of 45%. And so let me explain what a relative standard deviation means, and which is a relative standard deviation, or RSD. It's reported in percentage, and 2 RSDs, plus or minus 2 RSDs from the mean, explains 95% of the variability. So if we were to take an RSD of 45% times 2 gives us a value of 90. 90% of 50 is 47. 50 plus and 50 minus 47 would result in a range of 3 to 97 parts per billion. And what we see is that our actual range was from 2 to 102. So you can see how this relative standard deviation works. There are some other things I'd like to point out from this table that are significant. When we look at each of the results produced by the participants, they trended low, 50 versus 52, but notice for the 378 and the 580 that the participants' results were almost 100 parts per million below the value that they should. So there tended to be a low bias. The other thing that's significant is that the relative standard deviation remained pretty much consistent, 45, 44, 45 for each of these different measures. Well, all of these factors combined led us to some interesting conclusions. As I'd indicated before, we were looking to see whether we could use RMA results for the purposes of helping management aflatoxin risk. And what we learned was the producer actually owned these results for the purposes of crop insurance. And thus, in many cases, the grain handlers did not have the results similar to what we found in the bankruptcy case. Secondly, not everybody used or did the kind of frequency of testing as what we found in the bankruptcy case. We found that the sampling procedures did not conform to the lamb. And we found that if we wanted to rely on grain company results, we found that only 20% of the industry was currently testing with any accuracy. Our thought process made a pretty significant transition from the idea of how we can use other results to how we can assist the industry implement a quality management system to improve the testing capabilities. And so we introduced what's called a one-sample strategy, with the idea that you sample and test correctly once, and you can use these results for multiple purposes. And so this is something that was presented to us by our advisory committee, who essentially suggested the idea that, there are multiple tests that are being performed and samples that are collected from each truckload that crosses a scale. One would be for buying and selling. Another might be for crop insurance, and then a third would be collected by our agency for regulatory purposes. And the question was asked, why can't we use one sample for all three purposes, which is why we came up with this handle one sample strategy. And so the plan involved a quality system using approved equipment and processes for sampling and measuring aflatoxin, that needed to be accompanied with the appropriate training, as well as assessing the analyst's proficiency, and then our following behind them and verifying that, both visually as well as collecting retained samples that we would verify, as well as review their management and record keeping, and as needed to implement corrective actions. We proposed these ideas to the risk management agency, and which is kind of bringing us to this full circle, starting off with their need to have accurate testing and managing the risk of aflatoxin for crop insurance, and our need to ensure accurate testing for the purposes of ensuring animal and human health. And we captured this idea in this bulletin, where they agreed to collaborate in 2011 and subsequently in 2012 for succeeding years to adopt this one sample strategy, where they would accept the results of one sample with our oversight for the purposes of crop insurance. We would use it for regulatory purposes, and now the industry would be confident that their reports were good for purchasing. And thus we were able to reduce the risk for all parties interested in aflatoxin. And this program was further expanded in 2017 to include all mycotoxins. Well, I referenced the idea of a quality system to manage aflatoxin risk involving measuring, accurately sampling and measuring. And so the remaining chapters will go into some of those elements. And there are three in particular that I'll be talking about, the first of which is uncertainty. Uncertainty, as we would define it, is really a statistical bound that you would place on a result. So when you say, I have 20 parts per billion, with an uncertainty of 20%, one could infer from that, and this is important for your customers of your lab, that they understand what the results mean. 20 parts per billion with an uncertainty of 20% means that there's a 95% probability that the results will be between 16, the true results are going to be between 16 and 24. And that the 20 is our best measurement based on the sample that's collected and the analysis that was performed at the time. The issue of variability, of course, is one that we're trying to manage both in sampling and testing. And so when we consider variability, I want to reintroduce some of these statistical concepts. I've mentioned relative standard deviation already and explained how plus or minus 2 relative standard deviations explains 95% of the variability. And so let's look at our bell-shaped curve and review that for a minute. for a normal distribution. And as you look at this, the mean is represented by mu, and we see that one standard deviation above and below the mean explains 68% of the variability. Plus or minus 2 standard deviations explains 95% of the variability, and plus or minus 3 standard deviations represents 99.73% of the variability. And I will be, again, using these statistics, and we'll be using situations where we use 2 relative standard deviations and 3 relative standard deviations to explain our performance in a laboratory using a lab quality system. When we consider the sources of variability, you can see from this word cloud that it could be testing platform. There are those that are validated, and there are those testing kit platforms that are not validated. It's important that you know which ones are validated. There's the issue of particle size, and I'll be talking a bit about that in the next story. Certainly analysts and their qualification, the matrix that is being measured, as well as the things such as sampling amount, sampling patterns, sampling container, sampling device. All of these contribute to variability. So let's consider now some of the criteria used by the Federal Grain Inspection Service, which is another agency that I'm going to introduce into this presentation, of the United States Department of Agriculture in terms of their test kit validation procedure. The Federal Grain Inspection Service of the United States Department of Agriculture has published design criteria and test performance specifications for quantitative aflatoxin test kits. And their design and performance criteria look somewhat similar to the words on our previous slide in our word cloud. They're interested in grinding and homogenizing our sample, as well as having criteria for sample storage, the use of reference material, conditions for analysis or lab environment, as well as the clarity of written instructions and time for completion. They also have accuracy criteria in terms of minimum range and conformance, which I'm going to explain in this slide, where we have can see that 3 analysts must extract 7 separate samples for each concentration according to the test kit instructions, and each analyst must use a separate test kit manufactured lot. And so we're going to test the variability of analysts and kits, and at least 95% of the results, which we've already considered as plus or minus 2 standard deviations, which equates to 20 out of 21 samples for each concentration level, must be within the acceptable range published in the table below. So let's look at those acceptable ranges, beginning with aflatoxin at 5 parts per billion, which is in our left column, and our maximum relative standard deviation is 25%. And remember that 22 relative standard deviations explains 95% of the variability. So 25% times 2 is 50%. 50% of 5 is 2.5 parts per billion. Notice our acceptable range is 5 plus or minus 2.5 parts per billion, or 2.5 to 7.5. The table also shows what would be acceptable for 20 parts per billion, 100 parts per billion, 300 parts per billion, and notice that the relative standard deviation decreases from 25 at 5 parts per billion to 20 to 16 to 16 as the aflatoxin concentration increases. And this is easily explained just by the mathematics. Relative standard deviation is the standard deviation divided by the mean, and so while your standard deviation may stay about the same, although it actually increases as the concentration increases, we also see that the denominator increases and results in lower relative standard deviations. And this is a phenomenon that you would see and is consistent with what we've observed in our own laboratory. And so we'll be using these numbers, and I would also take time to point out the significance of this, because I believe it's also a good benchmark for your laboratory. Certainly when you're using reference material as your control sample, you would expect that your whatever concentration of your reference material, that you should certainly perform within the range published on this slide used to validate test kits. Returning back to our situation in 2011, one of the things that we found was that while there were 5 common test kits that are numbered on this slide, test kit 1, 2, 3, 4, and 5, we also found that the Federal Grain Inspection Service had only validated these test kits up to 100 parts per billion back in 2010. And our agency felt that there was a need for these test kits to be able to perform up to 1,000 parts per billion based on the level of aflatoxin contamination that we had seen in 2010. And so we proceeded to use the Federal Grain Inspection Service validation methodology and validate these 5 kits. And what we found is that they performed well at 59, 306, and 901 parts per billion, with the exception of test kit 3 in terms of accuracy. And this result had some additional benefits in terms of just managing aflatoxin risk in Texas. It helped us forge a relationship with the Federal Grain Inspection Service, but they increased the validation of kits from 100 up to 300 as a result of this. We also found that some of the kits that had been validated or at least approved were on the market and not performing according to specifications. So I think this helped through this type of third-party verification and validation performed by our agency, helped improve the overall quality of the kits on the market. And so that was a benefit as well. Now I'd like to go into greater detail with uncertainty, and I've already given you an introduction to this concept because uncertainty is a specific form of variability, and particularly it relates to your lab test results. It must be defined for the purposes of your customer if you're part of an ISO accredited lab, particularly ISO 17025. And it says that testing laboratories shall have and apply procedures for estimating uncertainty of measurement. This is something that your customer needs to understand when they get a result from you. What does it actually mean? And so there's 2 methods in which we can calculate uncertainty. One is the uncertainty budget method, using the Guide for Uncertainty Measurement, sometimes referred to as the GUM. The second is if you are using good control material, preferably reference material, you can just take plus or minus 2 standard deviations from your control material and use that to calculate uncertainty. But so let's look at the uncertainty budget method, because you'll certainly encounter this if you're pursuing ISO accreditation. And essentially what you do is list all the factors affecting variability. So again, uncertainty is part of variability in general. And then you take those various variabilities measured as your variance, add them together, use a root mean square, take the square root of, and calculate your standard deviation and then multiply that by 2 to get your coverage factor. And so this is an example of what that might look like, looking at the various techniques that we use or platforms to measure aflatoxin. And we also calculate uncertainty for a number of other assays that we perform. When we look at aflatoxin, the very top row, we see for HPLC, using reference material that measured 21.6 parts per billion, we had a relative standard deviation of 10%. And remember, for 20 parts per billion in the validation table, the acceptable amount was 20%. So you can see that we are performing at about half or 50% of what is the acceptable variability. So we're really doing a good job managing our variability. And then we multiply it times 2, which gives us our uncertainty. When we look at ELISA, we found that our RSD was 15%. And again, that would be 3/4 of what was the acceptable upper range of variability based on the test kit validation criteria. To reinforce the idea that I believe what the Federal Grain Inspection Service has published in terms of test kit criteria also provide, I believe, a reasonable benchmark for you as a lab that you should be able to perform within these bounds that are used to assess variability in test kit for it to be approved by the Federal Grain Inspection Service. Well, this leads us to our third story, which is going to be on sampling. So we've talked about the history of the office and how it led us to the conclusion of introducing lab quality systems and this concept of co-regulation, where we're using one test for multiple purposes, two of which were government purposes, one for crop insurance, the other one was for regulation in addition to buying and selling grain. We also talked about variability. Now we're going to talk, and particularly as it related to testing, and now we're going to look at variability in terms of sampling. This slide depicts the results of a study that we performed at 3 commercial maize mills in Kenya to support a marketing study by the International Food Policy Research Institute. And it was designed somewhat similar to the grain elevator study, where we were performing a variance component analysis, and for some equally important inferences that I'll present on the next slide. And it was at 3 mills, evaluating 3 trucks per mill, 10 bags per truck, 2 samples per bag, and then would evaluate each of those samples per bag twice, and then the extract twice, which would result in a variance structure presented on this slide, where we could look at the variability contributed by mill, truck, bag, in bag, as well as our analytical variability. And what we see is that for mill it was 1.9, which was the same for the grain elevator study that I presented before. For truck in here it's 4.1, and from the grain elevator study we saw truck contributed 9.1% of the variability. The biggest source of variability in this study happened to be with bag, and then followed by in-bag variability at 61 and 26% respectively. And then our analytical variability was 6%. And it's important to point out that this 6% was performed in our ISO-accredited lab on the campus of the International Livestock Research Institute. And what it represents is, in this particular study, we're really not testing the variability of our analysis. In fact, that was a very stable factor, and we were able to keep it under control such that we could focus on where the sources of variability were in receiving this grain. And we found that bag, and more particularly sampling of bag, contributed the greatest source of variability. And of course that's understandable. These are 90 kg bags, or maybe up to 200 bags per truck, and with that amount of grain there's a good possibility this could be from multiple fields, multiple hybrids, multiple farmers, multiple storage techniques. So it makes sense that the bag would contribute the greatest source of variability based on what we know about how this grain is harvested and delivered. We use these data to perform a statistical power curve analysis. And as you look at this table, the vertical or left axis is our power, represented as a fraction, but essentially the percent variability that is explained by the number of samples, bags that are sampled, which is on our horizontal bottom axis. And what we see at 80%, there's an intersection of 20 bags that explains about 80%, or more specifically about 83% of the variability. Now, in the past, we've talked about 95% variability. So if you look at this power curve, you see that it begins to flatten as it moves further right. And so at 90% probability, we would see that 25 bags would probably get us to where we needed to be. And then if you wanted to get 95% probability, then that would be 30 bags. And the purpose of this power curve is to find a balance between what we have in terms of our economic resources for sampling and the statistical certainty that we are seeking. And again, I want to point out that this is just one study. but it gives us an interesting view within the context of what had been sampling standards in East Africa. The 2007 standard would have required 14 bags to be sampled for a 20-ton truck, or one that contained 200 plus bags of 90 kg maize. So clearly our power curve would indicate that the sampling configuration or recommendation in the 2007 standard was too low. However, in 2017, a new standard was published that would recommend 50 bags per truck, and we see that to get to a 90% confidence or probability, our power curve would recommend about half as many bags as the new standard. And so the key is, when we talk about sampling, what kind of resources do you have available in terms of your sampling, and can you find the right balance? And what we found is that right balance seems to be somewhere halfway between the old standard and the new standard, based on this one study. Which leads to an interesting conclusion in one of the ways that we approach sampling as an agency. We sometimes look and ask the question, what can we feasibly do, and what can we feasibly expect the industry to do? And then from that, we define what is our level of confidence and its significance, and define the bound. And that enables us to approach regulating with a degree of certainty and uncertainty as defined by what is economically feasible. When we talk about sampling, of course, sample reduction is key, as characterized by this slide on grinding, and we recommend that the entire sample be ground, whether it be a 1 kg sample, which is what's prescribed for grain in the United States, what is prescribed for grain in Codex Alimentarius, what is prescribed by grain in the 2007 East African Standard, or whether it's 10 kilograms, which is what is contained in the new East African Standard of 2017. But whether it's 1 kilogram or 10 kilograms, we need to grind the entire amount. And I should explain, when I talk about this, that within our one sample strategy, we found that it was economically feasible for our industry to sample and collect 2 kilograms. And so, that's seemed to be the maximum amount that was economically feasible for our industry to work with. And they grind the entire sample, and we require that 70% of the material pass through a 20-mesh sieve. We grind and grind finely to preserve the representative nature of the sample as depicted on this slide. Now, the vertical or left axis gives us the number of particles in a 50-gram sample, and the bottom axis explains the percent overs on a 20-mesh sieve. And we have calculated, using regression modeling, the number of particles based on particle size, and produce this type of a slide, as you can see. And our far right vertical line presents the 70% remained on top or overs of a 20-mesh sieve. And what we see is that intersects our curve for particle number at about 120,000 particles, whereas the line to the left, with 70% passing through a 20-mesh sieve, we see that it intersects a curve that would be equivalent to 1.2 million particles per 50-gram sample. So this tenfold increase in particle numbers, by doing a good job grinding, retains the representative nature of the sample. We work so hard to collect the sample, the next thing we need to do is do a good job grinding. What we found, whether it's in Texas or Africa, without drawing attention to this, we find that people tend to undergrind. Sometimes I refer to this as just cracking the grain, and we would typically find 70% overs. And after concentrating on this, at least in Texas, we were able to get 80 to 90% through. And so we were able to boost our particle numbers well over 1.5 million in a 50-gram sample. We found the same thing in Africa. However, we find that the maize is harder, and so it's harder to grind. And so I'll talk about that in just a minute. Some other things that we found in common in terms of problems, whether it was in Texas or in Africa, first of all, is having a dedicated room to grind. Second, we commonly see an absence of engineering and personal protective equipment. Additionally, in our agency, we double grind. We do what I would refer to as a cracking with a roamer mill. We riffle the grain so we get equal subdivisions of that and do a secondary grind of a representative portion through a 1.5 millimeter mesh grinding sieve. And this is a wretch mill. It's important to clean the grinder between samples. We take the ground representative portion for analysis and do a 4-corner mixing to ensure homogeneity. And then finally what we found that works best in Kenya is a tabletop posho mill. This is actually Chinese manufactured, and it's a nutrition mill, and it does a very good job grinding. It can stand up to the rigors of having to work with the type of hard maize that is typical in Kenya, and I presume throughout Eastern and Southern Africa. At least that's the way it appears to me as I've looked at corn or maize from these other countries. And so now I'd like to get into Chapter 4, talking about reference material. And this is another really important part of our quality management system, sometimes referred to as the big three. We talked about uncertainty, and reference material is the means by which we ensure traceability. Reference material is traceable to a known result, ideally a certified reference material. And so we prepare this reference material, and for our purposes, we plot it on a control chart. And we analyze it daily whenever we perform this particular type of analysis. In this case, it would be aflatoxin. We have been producing control material for years as part of our laboratory activities, and recently achieved ISO accreditation in 2017 to the brand new ISO 17034 2017 standard for producing reference material. And we provide this reference material to our program participants in Texas as well as in East Africa. And when you produce reference material, there's some important criteria, including homogeneity, and it is measured by the Cochrane test to a 99% level of confidence. So again, getting back to the concepts of statistics and variability and how we define that. We also need to perform a stability test, and we performed this for our reference material at room temperature, both the type of room temperature we have here as well as what may be in an uncontrolled environment up to 30 degrees C. And we do that on a minimum of 5 samples at the time it's made, and then up to 6 months later. We plot the purpose of reference material is to make sure that your process is under control, as demonstrated in this slide for Company A and Company B. And we have 4 lines on the slide here. We have the blue lines, which represent the upper and lower control limit of the mean, which is our center black line, and then the red line represents our test results. The upper and lower control limits are defined as 3 standard deviations above and below the mean. And so we want to make sure that our control results are within plus or minus 3 standard deviations and fluctuate evenly above and below the mean. Now, when we look at Company B, we see that there tended to be a low trend for a while and then a high trend. I find that this is fairly common, whether it's in our lab or the labs that we work with, that sometimes we tend to get into a period of slightly low and slightly above type results. And now I'd like to get into the final chapter of our story, proficiency testing. And this is the third of our major quality system elements. And that is, and it provides us really a third-party verification that our testing is accurate. Our lab participates in as many proficiency tests as we possibly can. Some of the keys of proficiency testing are that the participants' identity remains anonymous and only they can see their results. Well, I say that with everybody can see everybody's results, but only we know who we are and can see what our results are. And when we compare to other labs, we don't know who the other participating labs are. We began offering proficiency testing in 2014 in Kenya, first with the commercial maize millers, and then we expanded it in 2015 to participate or to serve government labs within COMESA, which is a common market for Eastern and Southern Africa, reaching 5 countries in Eastern and Southern Africa. And here we see our APTECA proficiency test program. Aflatoxin Proficiency Testing and Control is what APTECA stands for. And we prepare these samples the same way that we prepare our reference material. And this represents our 4th sample that we worked around that we provided to our participants in Eastern and Southern Africa. We find that before we introduce a quality system, including the use of reference material, and in most cases, before we provide aflatoxin testing and qualification workshops, it's not uncommon to see the variability of these proficiency tests up to as high as 80%. And then after introducing a quality system, to see that variability cut by more than half. In 2017, we achieved accreditation to the ISO 17034 standard for proficiency testing, and this is the prescribed type of presentation of the results in this standard, where you see our bottom figure contains the results of each of our participants represented by a bar, and then we have a horizontal line, which is our assigned mean, so you can assess how many were above and below the assigned mean. And again, we see an overall trend toward under-reporting or under-measuring the aflatoxin level, which I'd already described as common in Texas, and we see that also to be a somewhat global trend. Our assigned mean is presented at the top of this slide, and it is 49.2 micrograms per kilogram. There are several ways in which you can report the mean. Either you can do a consensus mean or assigned mean. Our participants have asked that we use an assigned mean, so they want to benchmark their results against ours at the Office of the Texas State Chemist. The assigned standard deviation is somewhat unique, but is well within the standards and actually is preferable. And we use the Horwitz equation as presented here. And the reason why I say preference is preferable because it is not uncommon that the proficiency test provider standard deviation is about half of the composite standard deviation of the participants. In fact, that's a good benchmark to see. And so if we were to use our standard deviation, we would see that was too restrictive in terms of assigning lab results their Z-score. And if we use the consensus mean, that would be too generous. And so the Horwitz equation has been around for years, decades. And so that's how we calculated our standard deviation. And that's important because we calculate a Z-score, which tells the lab how they performed by taking their result minus our result divided by the assigned standard deviation. And we see our Z-scores presented in this far right column. And a Z-score of 2 or less suggests that indicates that the mill has done a satisfactory job. Whereas from 2 to 3, the results are questionable. Greater than 3 is unsatisfactory, which would lead the lab to want to take a corrective action, including a root cause analysis. And one of the reasons preserving the anonymity of participants is good is because nobody wants others to know that they had a Z-score greater than 3. And nobody will other than yourself. There's great value to know if you get a Z-score greater than 3 what the problem is. And because you do a root cause analysis, nobody establishes a lab to produce a bad result. Everybody wants to produce a good result. And then this is one of these unusual situations. A Z-score of 0 indicates perfection. So if anybody, as part of a proficiency test, refers to you as a 0, that's another way of saying you're perfect. We offer this aflatoxin proficiency testing program globally. And at the top of the slide, we have the URL where you can go look at this. And it's at pt.tamu.edu. And then if you look to the bottom of the slide, we have 2 tabs that are present and are available. The first one you can press on, and that's how you would register. And what will present itself is a PDF form that you can fill out and then email to our office. It's really important that you complete it thoroughly. In particular, the address needs to be a mailing address, ideally with a physical location, with which you either receive DHL or Federal Express shipments. In general, with the proficiency testing program, whether it's ours or anybody else's, only those who participate have access to see how the rest of the world is doing in terms of their results. And with that, we'll entertain questions and look forward to you participating in this aflatoxin proficiency testing program offered by Texas A&M. And I think I failed to mention that we provide this at no cost. Essentially, we ship the materials, prepare the proficiency testing program, and ship it to you for free. However, you are responsible for bearing the cost of doing the test and entering these results into the program. Our next round of this program begins in July. We'll be reporting the results out in October, and you'll be able to see, based on this website, each year we post when the rounds are offered and due when you participate in this program. And we'll start with our question and answer session. And Bola, you'll be leading that.
Well, Dr. Herman, thank you very much for a very insightful and stimulating presentation. I particularly appreciate the fact that you shared the history of the Office of the Texas State Chemist and how you developed certain testing criteria and how you provided certain measures to ensure due diligence during testing. So I have a couple of questions, and then we'll see who else has questions. The first question I have is, for some of our partners in the countries where we work, they might look at some of the measures you've put in place and think that they're very onerous or very challenging to comply with. So do you have any examples of a lab that you had worked with in Africa or in another country that initially had very high variability in their testing results, but as they over time followed the procedures that you recommend, were able to become much more precise in their procedures, in the analysis?
Yeah, that's an excellent question. And what we found actually is about 80% of the laboratories, whether it was in Texas or in Africa, before we implemented this program, had tremendous variability. And after implementing that, we found that based on our proficiency testing, fewer than 5% were experiencing this huge amount of variability. And so I'll begin with an example of 2 mills, and I won't necessarily provide their names. And we have 80, and I might be stuck on this 80%. We had 80% of the commercial maize milling capacity in Kenya participate in this program after its introduction. So none of them found it to be too onerous. The way we began this process was very similar to what we did in Texas, where we would take a sample and ask people to analyze it. Actually, I think we had 3 samples, similar to Texas. And the first mill that tested it, their results were really poor. And the reaction of the miller was perhaps common to some of our early participants. He was really quite upset And understandably so. He was investing a lot of money to get test results, and he thought he was getting good test results. And so he invited me back to the mill, and you might call it an invitation. You could call it a demand that I do not leave until we solve this problem and their results suddenly start to produce what he's paying for. The other establishment was more lackadaisical, which we sometimes see. They actually charged us for this study, and we gave samples of like 5, 50, and 200 parts per billion, and they produced a result of a 9, a 10, and 11. And they didn't seem all that concerned and just kept going on their way. It took a little bit of a different approach to get them to begin to implement a quality system. So everybody's unique, but the ability to implement these quality systems, really, when you consider the investment in testing for aflatoxin, it's so expensive to do it incorrectly. Not only are you operating on bad data, but you're wasting all that money in the test, hiring an analyst, reagents. And so relatively speaking, I would say implementing a quality system with the criteria that we've discussed briefly is actually is a huge cost savings, because you're actually getting what you pay for.
Yeah, thank you very much. Second question before we invite others to, before Jim asks the questions that are being submitted, is what about sample storage? And would you mind sharing your recommendations for storing grain samples, milk samples, blood samples for aflatoxin analysis, please?
That would be fine. Particularly what we find at our laboratory and typically in the States is that the moisture level is at an acceptable level of our sample, and so we don't ever experience an increase in aflatoxin. In terms of sample storage in a developing country, I would suggest the first thing you need to know is what your moisture content is. And if it's high, then I think the value that's being used in places like Africa, and you have a harder grain, is I believe it's 12 or 13%. And in the States, it's 15%. But to get it dried down, if you're not going to grind it right away, and then keep it at a lower temperature, because the mold grows and then also produces the potential, has the potential of producing increased toxin. We don't test milk samples, but I'd imagine, again, you want to get those tested right away. Probably the same with, certainly the same with blood, and keep those cool. I don't have a prescribed temperature for those. But the key is to get them sampled, analyzed right away.
Thank you very much. We do some milk testing, and we keep the milk samples refrigerated, and like you say, we try and test them as quickly as possible on the same day when we can. So I'm going to turn it over to Jim, and he's going to read through some of the questions that have been posed.
Yes, thank you for sharing questions, everyone. I don't know if I'll have time to get through all of them, but let's start with the first one from Kazita Nishimwe. His question is, any advice regarding low kits, for instance, water-based kits, as there are many different kits on the market?
Absolutely. Absolutely. What I would recommend is you go out to the Federal Grain Inspection Service approved test kits, and they validate those and publish those kits, and there's quite a few that are available. And I understand the desire of using water-based versus organic solutions, because the latter are more expensive. My concern about water-based kits, particularly as we get outside of a really well-controlled lab environment, is that you have pure water. One of the experiences that we found, for example, in Kenya, is people might buy distilling units or purchase distilled water. And when we were using a fluorescence-based kit, we still saw background fluorescence because the water was not pure. And so that would be my one concern, and why it's so important to use reference material, because you would be the first thing you detect is variability in the kit if it's related to water or anything else. So that's why reference material is so important. So again, there are some good validated water-based kits, and they would be available on Federal Grade Inspection Service approved test kit. And so all you'd have to do is type that into your Google search, or whatever search you use, because I'm not endorsing Google per se. And you would find that published on the World Wide Web.
Thank you. Okay. I'm going to go ahead and read the next few questions and let both of you respond to them. So first one is about the sample amount. For the sample amount, does it have to be 50 grams, or can one use a different amount? The next question is about testing in milk. I wonder if you would consider to test aflatoxin in liquid food like milk, and is the procedure different from maize testing? And then our third question, why are there differences in the limits for some grains between the EU and the USA? Which one should countries who do not have their own limits use?
Well, those are excellent questions, and I should have written all three of them down. Let me get my glasses, because I was thinking of the answer of each one of them. 50 grams, as opposed to what, 5 or 10 grams? Again, using the same concept of doing a good job grinding. Ideally, the larger the sample that you can extract, the better. 50 grams is what we use as a regulatory agency. There was a discussion of using 200 grams using a slurry method, but we found that the labs that employed that actually experienced much greater variability. So we see no benefit to going over 50 grams. Now, if you do a 4-corner mix and have a real homogeneous sample, could you get by with 10? If that's going to save you money, but I would prefer 50, because again, it retains a representative property of the sample. The next question involved kits and milk versus, was it kits, or let's see, milk versus maize. And we'll let Boda talk about that, but I would point out that these are entirely different levels and typically measuring different things. For example, in maize, at least our agency and much of the world likes to look at total aflatoxin. Although if you go to Europe, they really focus on B1. And their level, I believe, is 4 micrograms per kilogram, where ours is 20. And then versus milk, where our level of acceptability is 0.1 micrograms per gram B1, or M1, excuse me, M1, where I believe in Europe and other places in the world it's 0.01 micrograms per gram, or 50 parts per trillion versus 500 parts per trillion. But irregardless, you're going to be using a different technique when you measure milk versus the maize. Oda, would you like to make some comments on that?
Yes, certainly those methods are different. And for milk, you can use HPLC, you can use ELISA-based methods. If you want to send us an email, I'll be happy to share the procedures with you. Dr. Herman also alluded to the differences between forms of the toxin, and I think this is extremely important, because in many of the countries where we work, or at least in some of them, there have been reports that milk is unsafe because of high levels of aflatoxin. And the information generally is extrapolating the toxicity of the B1 form, which is far more toxic, to the M1 form in milk. And this is something that we're working on to actually quantify the toxicity of the M1 form, which of course is well known to be far less toxic than the B1 form. But we do have the procedures, and I'll be happy to share them with you if you contact us. Thank you.
And so I'd like to say a few words about the difference between the US and EU and what should somebody in a developing country adopt. And, you know, sometimes we would refer to Codex Alimentarius, and interestingly, Codex has not had a standard for aflatoxin per se because there are such differences, let's say, between the US and EU. And what you need to consider also is the exposure level or likelihood. For example, the people in Africa certainly consume at least double the amount of maize, for example, than we do in the States. And so our limit for human consumption is 20 parts per billion or 20 micrograms per kilogram. And in some countries where there is actually a standard, although it is not readily published or transparent, we see that in Africa, some of these countries, the level is 10 parts per billion, which I think is a good number since that's essentially half of what the US is, but Africans are consuming at least double what we are. At some point in time, there comes an issue of what do you need to keep the market moving? And as a regulator, I'm very sensitive not only about protecting food safety, but also about keeping the market moving. And our Food and Drug Administration is also very cognizant of that as well. I mean, the only thing worse in food that would be marginally safe is no food at all. And so if we set these limits so rigorously that we're going to be unable to use our product when in fact it may be acceptable, but not as safe as we'd like it to be. You know, we need to have systems that are appropriate to address and balance these needs between food supply and food safety.
I think that is an excellent comment, because I've been in some countries where they've set even more exacting standards than we have here. And when I think about the value chain involved in producing these foods, processing these foods, I have a significant concern about the compliance burden and the cost of compliance. So Dr. Herman's comments on combining or merging, balancing the need for a safe food supply with a need to provide some food that may not be as safe as we would ideally want it to be is exactly spot on. Thank you.
All right, we have one final question that we'll take, and then we'll conclude this webinar. And I also want to remind people of the image on the screen of the website, which, as you mentioned, is open for about 1 week for people to register. And you can see the password is also there at the bottom of this slide, temp password.
Could I
yes.
just qualify that? You can register at any time. It'll always be open for registration. What will be open for the next week is giving you a password, an ID and a password that you can look at these results of past participants. And after you register, you will be given your own ID and password such that then you will be able to access all of this. But we typically only share this with people who are participating in the PT program. So we try to prevent free riders. So this is really a chance for you to see what we have available. And then you won't be able to see the results in the future because unless you enroll, but then you'll have constant access. But registration is always open, but we'd sure like to see you register as soon as possible because our next sample will be mailed in about a month.
Okay, thank you for that clarification. And also I want to clarify that it's free. So this is an amazing opportunity for you. Our final question is from Gutema Dinkisa. For aflatoxin analysis, what is the best mobile phase using HPLC method to achieve the best sensitivity? Are binders applied in the food processing for detoxification?
Well, yes, well, I didn't pull out our, I should have had our SOP, but we'd be glad to share it for HPLC. But I believe it's either methanol or ethanol mixed with water. One thing that's unique about HPLC versus the other methods, and what we do is we have a photo-enhanced derivatization technique. And I believe that is what enables us to get such tight control over our variability versus just going directly through, and is possible to do with your high performance liquid chromatography, directly to a fluorescence detector. So that intermediate step of photo enhanced derivatization we found to be very, very helpful. And then we'd be glad to share our HPLC method.
All right, great. And I believe, Bola, you'd like to make some final comments?
Yes, first of all, I'd like to thank Dr. Herman for an excellent presentation. Like he mentioned at the outset, this is likely to be one of a series of seminars, so we will work with him and we will let you know when the next one will be coming up. The Livestock, Feed the Future Livestock Systems Innovation Lab here in the Institute of Food and Agricultural Sciences at the University of Florida will continue working on aflatoxin. We have a number of projects that are aimed at determining the sources of high levels of contamination in some of our countries. We have an initiative that is going to look at what is the true link between M1, the M1 form, which is usually in milk, and cancer. And as I mentioned earlier, with some of our countries, we've conducted aflatoxin mitigation and prevention workshops, and we'll be working with the countries on raising awareness, on risk communication, developing risk communication strategies. We've set up some labs for aflatoxin testing, and so we'll be working with them to comply with Dr. Herman's recommendations and so on. So I'd like to finish by thanking you all for calling in, and I look forward to your participation at our next webinar. Thank you.
Yes, thank you to everyone. And as I mentioned earlier, this recording will be made available on our website. So this is the conclusion of today's webinar, and we hope to bring you more in the future. And we're saying goodbye now from the Feed the Future Innovation Lab for Livestock Systems. Thank you for participating.